So now, so today we'll start some basically theorem. And okay, basically there are the two theorems. One is okay, theorem, and this theorem says that a non-empty closed convex set suppose S, which belongs to Rn, and this is bounded. This is bounded, and this is bounded from below. Okay, bounded from below or above one side bounded. Basically, the non-empty closed convex set S in Rn bounded. If we say below or above, तो हम दोनों कंडीशन ले लेते हैं, below or from above. Okay, so any non-empty closed convex set which is bounded from one side, and this has at least one extreme point. So this has at least one extreme point. Okay, so to prove, so this proof will be proved by the mathematical induction, and the mathematical induction means here we take the this theorem is true for we check that this is true for n equals to 1. Will try to prove that this n equals to n plus 1. This formula is also true. Okay, so here if we take one dimension, so you know that since this S is closed, S is closed and bounded, if you take from below, that is if we take n equals to 1, n equals to 1 means one dimension. One dimension is this is your real line. Okay, so this is your 0. Okay, so if we take any, this is bounded from below, and we take any closed convex set. So suppose this is bounded from below. Say this point is suppose alpha. Okay, and suppose this is bounded below, and this is tends to infinity. Okay, so this set, suppose this set is your S, which is a collection of all x such that this x is greater or equals to that alpha, and alpha belongs to R1. Okay, so you know that this point is alpha. Okay, and this is bounded from below. So here there exists, if this set is closed and bounded below, then you see that here one point, that is alpha, is your extreme point. Okay, so this means this theorem is true for n equals to 1. This means this theorem is true for one dimension case. Okay, so here for n equals to 1, we take this closed set S. This is collection of all x, such that our x is greater or equals to alpha. Okay, because x, so that is x, such that this x is alpha. And here alpha, what is alpha? Alpha is one dimension real number. So we can write R1. Okay, this is your set S. Okay, and here you see that this alpha is an extreme point. So here we say that obviously this alpha is an extreme point of your set S. Okay, so this means this theorem is true for n equals to one dimension. So and the theorem is true for one dimension case. Okay, so now we suppose that this theorem is true for n equals to n. Okay, so we write here, let us now assume that the theorem is true for n equals to m. Okay, so we shall then prove that it is true for more dimension, that is n plus 1. Okay, so if you have to prove that this is also true for n equals to m. Okay, so now if this theorem is true for n equals to m, this means you assume that any set, if you take this set S, and this is suppose this is subset of m plus one dimension, and we have to prove that this set, which is a closed and bounded stream point, there exists a stream point. Okay, so here this S is subset of Rm plus one dimension, and since this S is closed, bound below, this is bounded below, from bounded below. So here we can say that there exists a boundary point suppose we take W, okay, by using supporting hyperplane theorem. So there exists a boundary point W of this closed set S, and by supporting hyperplane theorem, by supporting hyperplane theorem, there is a hyperplane, suppose if we define that hyperplane is H, and this H is collection of all X such that A transpose X that equals to B. Okay, so this hyperplane of set S at the point W. Okay, so this means this says that this is closed and bounded below, then there is a boundary point W, वहाँ से आपके hyperplane होंगे. Okay, so if we assume that any T star be the intersection of the set S and the hyperplane H Okay, so this means this says that any set okay, which is bounded below, this is your set, which is subset of R and plus 1. Then there exists a boundary point. So यहाँ पे एक boundary point होगा. That point is W, and there exists a hyperplane. Okay, this hyperplane and this hyperplane H. And what is the dimension of that hyperplane? That hyperplane, the dimension of that is 1 less than the dimension of this set. Okay, but this is suppose this is your R2. Okay, so this means this is your straight line, one dimension. So here this is Rn plus one. So this hyperplane is subset of your Rn. Okay, and this is the intersection point of this hyperplane and your set, and this is your intersection point is suppose T star. Okay, so now this is say that the intersection of H and S. This is your T star. T star be the intersection of that point. Okay, so this means this is intersection point. So that's why this is non-empty set. So T star the uh, this means you say that T is then a non-empty. Okay, closed bounded set, which is bounded from below and is of dimension is a dimension that is n. Okay, so therefore, by hypothesis, this T star, this is the intersection point of S and H, as an extreme point, as an extreme point. Because we say that this is true for n equals to n. So this means n equals to n, and this closed non-empty set, okay, T star of dimension n. So this means this has an extreme point. Okay, so by hypothesis we say that this has an extreme point, and now we claim that this extreme point, that extreme point T star, extreme point of this T star is also, this T star is also extreme point of S, is also an extreme point of this set S. Okay, so here we claim and we try to prove that this is true. Okay, so this means to prove our claim, for this claim, we prove our claim. Let us suppose that, there is X star is an extreme point of T star. Okay, so let's suppose that this X bar is an extreme point of T star, and which is this X bar is not the extreme point of that S. Okay, तो हम ये लेके चलें और फिर देखें कि हमारा रिजल्ट क्या कंट्राक्ट तो नहीं हो रहा है. Okay, so to prove our claim, let us suppose that this X bar is an extreme point of our T star. So T star, and which is not an extreme point of S. Extreme point of your set S. Okay, so here this is any, we take here X bar, and this X bar be the extreme point of this set T star. Okay, so now we know that if any 2 points, suppose if take any 2 points, suppose x1 and x2, 2 point, if we take it on this is belongs to your set S, then the convex combination of these 2 points is equals to suppose x bar. Okay, so x bar is the convex combination of these 2 points. Okay, so by the supporting hyperplane theorem, you know that this A transpose of x1 and A transpose of x2 both are greater or equals to your b, because this is your hyperplane, this is your hyperplane. So these 2 points, okay, so when we take A transpose x1, this is greater or equals to b because this lies in one of the half plane. Okay, so in next page, then this x bar, which is the convex combination of x1 and x2 points, where this x1 and x2 belongs to set S, and say theta is lies between open interval 0, 1. Okay, so here, if we take this is by supporting hyperplane theorem, supporting hyperplane theorem. Okay, तो इक्वेशन नंबर उसमें देख लीजिएगा क्या इक्वेशन नंबर समथिंग जो भी सॉल्व कराया होगा. ओके, तो वहाँ पे A ट्रांसपोज x1 is greater or equals to B. Okay, for any, and A transpose x2 is also greater or equals to B. And since this A transpose x bar, and x bar be the we've taken this extreme point of T star, and which lies on the hyperplane, so this satisfies our this equation B. Okay, so since A transpose x bar that lies on the hyperplane, that is equals to B. Okay, so we have this B. B means A transpose x bar. And what is the x bar? X bar is A transpose x bar is a convex combination of these points 1 minus theta of x2. Okay, so this condition holds because this equals to this condition holds because if we try to solve this equation. Okay, so this satisfies if and only if, and this will hold if and only if and only if this A transpose x1 this equals to suppose B, and A transpose x2 suppose this equals to also B. Okay, so if this equals to B and this is also equals to B, then this condition holds. Okay, so here you can say that, in other words, if and only if this x1 and x2 this belongs to your because if these two conditions satisfies, this means x1 is lies on your hyperplane and also x2 is also lies on hyperplane, and these 2 points are the intersection of your hyperplane and space S. This means this is all belonging to points T star. Okay, so this means this x1 x2 belongs to T star, so which contradicts our result, which contradict that this T star is that contradicts that x bar, basically that point is x bar, contradicts that this x bar is an extreme point of this T star. Okay, so this means you say that finally, hence the extreme point of this T star is also an extreme point of S. Okay, so thus you say that your theorem is true. So thus if the theorem hold for this n equals to m. So it also holds for this n equals to m plus 1. Okay, and we have seen that it is also hold for n equals to 1. So hence, by induction, we say that this theorem is true for all n is greater or equals to 1. Okay, this means this is true. So here, every supporting hyperplane of a non-empty compact convex set S contains at least one extreme point of S. Okay. So this is a simple theorem, and there is more theorem which is also depending on this theorem. And this theorem says that every point of non-empty closed convex set in a closed bounded convex set S, it belongs to Rn, is a convex combination of its extreme points. Okay, so this says that every point of non-empty closed bounded convex set, it belongs to S in Rn, is a convex combination of its extreme points. Okay, so this theorem is, of course, based on this previous theorem, and we try to say that that point is maybe a boundary point or an interior point of that set as. So, okay, so next page, the second theorem. And this theorem says that every point of a non-empty closed bounded convex set, suppose S, which belongs to Rn, is a convex combination of its extreme points. Okay. The proof. This proof is also we use this mathematical induction. Okay, we say the induction on the number of dimension n. So if we start with suppose n equals to 1, and where S is suppose closed and bounded. Okay, so this means you take any set S on a real line, and this is closed and bounded, and this is your set S, which belongs to R1 space. Okay, so this is a set of R1. Huh. So here, this point is A, this point is B. So suppose if we take this closed interval AB. Okay. So you know that this says that if n equals to 1, this means you have a one dimension space, that is set S is closed and bounded. Bounded. We take that is interval AB, whose extreme points are whose extreme points are extreme points are basically A and B. So you know that, you see that here, and every points of which means this interval, every point only, that point is the convex combination of these two extreme points. So this every point of which is a convex combination of A and B. Okay, so hence the theorem is, hence the theorem holds for n equals to 1. Okay, so now we assume that this theorem is true for n equals to m, and we try to prove that this is also holds for n equals to n plus 1. Okay. So suppose that the theorem holds for n equals to m, and we shall prove that it is also hold for one more dimension n plus 1. Okay, so if we suppose our S be the subset of R and m plus 1 dimension, okay, and any point, suppose x naught, be any point in S, any point in S. So this means you have take the enclosed set S, and this is a subset of R n plus 1, and here you take in point x naught, which belongs to that set S. So this means you prove that if this set has suppose any extreme point and this x naught point, so this x point, x0 point may be on its boundary point or its interior point. And if this is a boundary point, so you have to prove that this is a honest combination of any x naught which is lie on the boundary. So this is your honest combination of extreme point of that set S. And if this point is a interior point, so any interior point can be expressed as the convex combination of its boundary point, and every boundary point is also written as in the form of extreme points. Okay, so here this means there are two cases as arises. So first one is this x naught point may be on this interior point, or this is or any boundary point. Okay. So x naught be any point in S. Okay, and now we assume that there are two cases. So now this x naught is A. This x naught may be a boundary point, of S. Our second one is B. This is an interior point. Okay, so here if we deal case first, so if this is a boundary point, so let x naught be boundary point, be a boundary point of set S, and suppose your H, which is the hyperplane, collection of all x, A transpose x equals to B. So this is your hyperplane. This is hyperplane. This S be supporting hyperplane. The supporting hyperplane at that point x naught. Okay. In first case, this first case A, suppose there is a boundary point, so there is a hyperplane H which is passing through this point. Okay, so this is case A and this is case B. Okay, so x naught is lie on this boundary point. Okay. So then you know that the set intersection of these two sets H and S, that is T star. So the set this S intersection H is then a non-empty is then a non-empty and bounded and also closed bounded set of dimension m, and we assume that this is true for this dimension m. So we say that by hypothesis, therefore, every point of this intersection set is convex combination of convex combination of extreme points, because we assume that this is true for n equals to 1 n. So it's extreme point. This is true for extreme point. Okay. So but as shown in the previous theorem, so okay, so we write here, but as shown in the proof of previous theorem, but as shown, but by the previous theorem, by the previous theorem, you know that an extreme point is of this S intersection H is also an extreme point of S, an extreme point of S. Okay, so this means you say that your X naught is a convex combination of extreme point of given set S. Okay. So for case B, so if we assume that this x naught B is an interior point of S, then any line joining this x naught point, okay, line with the boundary point, suppose here if we take x1 point is boundary point here and x2 point is boundary point here. So this x naught point can be written in the convex combination of these two, x1 and x2, that is boundary point. And from case one, you also know that this any boundary point can be written as a convex combination of its extreme point. So that's why any point x naught is a convex combination of its extreme point. Okay. So if this point is an interior point, so we assume that x naught be an interior point of S, so then any line, so this x naught intersect S in a line segment with boundary point x1 and x2. Okay. Therefore, x naught can be expressed as a convex combination of x1 and x2. Okay. And
Hello.
Case B. Let x naught be an interior point of S, then any line through x naught, any line through x naught intersects S in a line segment with boundary points x1 and x2, and therefore x naught can be expressed as okay, expressed as a honest combination of x1 and x2, x1 and x2, and इसके आगे भी एक लाइन और लिख लें. Now since x1 and x2 are also boundary points of f, A, now since x1 and x2 are also boundary points of S, by case A, they are convex combinations of the extreme points of S. Okay, extreme points of S. Points of S. Hence, x naught is also a convex combination of extreme points of S. Okay, तो ये थोड़ा सा थियोरेटिकल आपके एग्जांपल्स थे. Okay, now next page पे चलें और शायद कुछ चीज़ यहाँ डिस्कस में याद भी आ गई. कुछ क्वेरी थी आप लोगों की कुछ इस तरह का कि आई थिंक सपोर्टिंग हाइपरप्लेन थ्योरम में कुछ क्वेरी थी आप लोगों की, शायद कुछ व्हाट्सएप मैसेज आए थे. इसमें थी बाकी बात तो नहीं मेरे से सब. सपोर्टिंग हाइपरप्लेन थ्योरम कुछ आप लोगों की कुछ क्वेरी थी. मेरे ख्याल से समथिंग दिस वन ए ट्रांसपोज बी को लेकर के एंड सम मेरे ख्याल से मैसेज एक सेकंड में मैसेज थोड़ा सा देखता हूँ. एक सेकंड. ओके, तो क्विकली हम बताते हैं कि प्रॉब्लम मुझे मिल गई. सम स्टूडेंट्स हैव अ क्वेरी रिगार्डिंग this portion. How can we write these two are same basically? Okay, and the terms is okay. So in our separating hyperplane theorem, this is your S and this is any boundary point, suppose it W, and there is any Y which is not belonging to S. So there exists a hyperplane that passes through that point. Okay, so this says that this boundary point has basically minimum distance. Okay, so distance this point is here. Okay, not here. So if you're using supporting hyperplane theorem and suppose S be a non-empty R space, that is R space, and here any point that is Y which is not belonging to that on except S. So there exists basically boundary point W, which is uh, that distance is the minimum one, which is quality distance. And of course, there is a hyperplane H, and that hyperplane which passes through that point completely divides this array space into two half spaces, and where S is lies in one half space. Okay, so in this theorem, the proof of in this theorem, you have some query regarding this students regarding this W minus Y transpose and X minus W. Okay, and there is another term is W X minus W transpose. Okay, okay, and W minus Y. Okay, and we and sometimes are opposed here and here, and we write combine these two terms and we write 2 theta and W minus Y transpose X minus W. Okay. So basically, in the justification of that, we uh, uh, give you some A and B type of matrix multiplication and that type of this thing. So you know that A transpose B transpose, if we take this transpose, okay. So this becomes this is B transpose, this is B transpose, and because if A and B are two matrices, if A and B are two matrices, then AB, you know that AB transpose that equals to B transpose A transpose. Okay, so by using that formula, this becomes B transpose and A transpose transpose. And also you know that the transpose of transpose any matrix is equals to A. Okay, so if this matrix of any dimension, suppose in cross and matrix, okay, so if n cross n matrix, then A B transpose, okay, so this equals to B transpose A transpose, and A transpose that equals to A. Similarly, here if we write in here, because we defined here, this is a vector A. Okay, so this is A transpose B transpose equals to B transpose A, or you can say that A transpose B transpose this equals to B transpose A. Okay, so this is true for matrix case. This is true for matrix case, or you can write here A transpose B. If you write matrix form, capital letter, so this equals to B transpose A. If A and B are the matrices of order n cross n. Okay, so this is true. But here in our case is this is a well-defined point in because this point is given y belongs to this thing. So suppose if you take y be a point, suppose if you take those components are y1, y2, and y3. If we take simple Rn and n equals to 3, suppose. Okay, so here this is your y point, given point. What is the W point? W point is also a three-dimensional space. This is W1, W2, W3. This is transpose. Okay. So here this is a column vector here. That's why this is a column vector, that's why these two terms are same. Because if you want to prove that and want to know what is the value of this function. Okay. So here you also know that what is A here. So here we assume that this A is a vector. A is a vector basically from this to this direction, and this is a W minus Y. W means this is simply W1 minus Y1 component, W2 minus Y2 component, and W3 minus Y3 component. Okay. So this is for vector A. This is vector A. Okay, and if any x that belongs to that set S, and x has value is suppose x1 and x2 and x3. Okay, so what is this? This W minus Y transpose, if we take this term W minus Y transpose with product of x minus W. What is the value of this? W minus Y means your component are y1 minus y2. Okay, this is transpose. This means this term is w2 minus y2 and w3 minus y3. Okay, so this means this transpose. And what is the column vector of this x? Suppose x1 minus w1, okay, x2 minus w2, and x3 minus w3. Okay, so now if we multiplying here, so you get here w1 minus y1 into x1 minus w1 plus this is w2 minus y2 x2 minus w2, okay, plus w3 minus y3 into x3 minus w3, and basically this matrix have order 1 cross 3 and this is 3 cross 1. So this result is basically this is your final result, and that answer is your belonging to real number, that is R1 space. Okay. Similarly, if any student has computing this value, this value is x minus w transpose and w minus y. Okay. So here, this is of dimension. This is of dimension. This is, or if you take n dimension, this is n cross 1 and this is 1 cross n, 1 cross n, n cross 1. This is also a real number. Okay, so in real number, so that's why both are same, because the dimension of product of this is one dimension. So that's why these two are same for in one dimension case. That's why we write here this w minus y is A transpose. So we write A transpose B is same as we write B transpose A, because this is so belongs to real one, and this is also belongs to real one, and but in matrix form, this transpose equals to this thing. In matrix notation, this transpose equals to this thing. But here, this is the real number one. So the transpose of that is also a real one. That's why these two are same in this particular scenario. But in matrix form, this is true. If this is a matrix of order m cross n, then these two are not equal. But here, this is a real number, and this is also product of this is a real number, and that two real number are same, because if the any real number, suppose 5, if we transpose that number 5, this is 1 cross n matrix, this is a simple 5. Okay, so that's why these two are same. Here, if we try to product of these two, this becomes x1 minus w1, where the second term is this is the product of x1 minus w1. This is x2 minus w2, x3 minus w3, and product of this w1 minus y1, w2 minus y2, w3 minus y3. So this product is equals to x1 minus w1 into w1 minus w1 plus, and so on. And you see that these two terms is also same, because this is also belongs to R1. This is a real number, this is a real number. That's why we write here this is 2 times. Okay, so some confusion in there, I know, because this formula is valid, this formula is true for the matrix case, when this A and B are matrix of dimension n cross n. But here, this is a column vectors. That's why here the product of these two is a real number. So that's why the transpose of that is also equal to that real number. ओके, तो इसलिए इस केस में ऐसा है, तो उसमें कंफ्यूजन होने की बात नहीं है, ये तो एक जनरल फॉर्मूला हमने बताया केस, ठीक है। तो जिन स्टूडेंट्स को क्लियर था उनको कोई बात नहीं, किसी को कंफ्यूजन वहाँ पे है तो आप उसे यहाँ पे क्लियर करें। तो आज इतना ही करते हैं, नेक्स्ट हम स्टार्ट करने वाले थे कॉन्जुगेट फंक्शंस, तो हम कल करेंगे, ठीक है। आज इतना ही करते।
सर हम लोगों का रिजल्ट कब आएगा?
रिजल्ट आएगा थोड़ा इसमें डिस्टर्बेंस चल रही है थोड़ा, तो रिजल्ट आ जाएगा, क्योंकि अभी एग्जामिनेशन भी आपके समय है, तो अभी आपके सेशनल के भी मार्क्स हमें देने हैं और रिजल्ट आ जाएंगे। हमारा पेपर था कोई आपका?
डिफरेंशियल इक्वेशन का था।
ओके, इसका रिजल्ट नहीं आया ना?
नो सर।
ठीक, ट्राई करते हैं। आप तो मान के चलें कुछ दिन, अभी यूनिवर्सिटी ने भी हम लोग को सब कुछ समय दिया हुआ है, तो मान के चलिए 30 अप्रैल तक या फिर 10 मई तक, क्योंकि अभी सारी चीज़ें एक्सटेंड होंगी, क्योंकि अभी कंडीशन थोड़ी फेवरेबल नहीं कर रही, तो कुछ समय अभी आप लोगों को भी दिए जाएंगे और हम लोग को भी दिए जाएंगे, बिकॉज यूनिवर्सिटी बंद है और हम लोगों को बिना यूनिवर्सिटी गए इंटरनेट के ही थ्रू हम लोग मार्क्स अपलोड करेंगे। तो जब वो परमिशन मिल जाएगी तभी जाकर के हो पाएगा। तो कुछ दिन और वेट कर लें, कुछ दिन वेट कर लें, जहाँ परमिशन मिलती है तुरंत हो जाएंगे। ओके, ठीक।
ओके सर, थैंक यू सर।
थैंक यू सर।
थैंक यू।
थैंक यू सर।
Thank you, sir.